So welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 8, that is problems related to sum of vector spaces, direct sum of vector spaces, direct sum decomposition of vector spaces, and dimension equality. So let us start with first question, which we would like to discuss. So, question 1. Determine which of the following examples of the vector space R3, respectively R4, are the direct sums of the following subspaces U and W. So these are two subspaces of R3 that A such that ABC in R3 with A plus B plus C is 0, and W is subspace in R3 such that for any vector ABC in R3, A plus 2B is 0. And this is in R4. A plus C is 0 and B plus D is 0. This is in R4. And W is A plus B is 0 and A plus D is 0. So in second vector subspace here, we do not have any condition on C. So C can take any value in R. So let us start the solution. So what we want to check is to check that this U plus W is a direct sum or not. So what we need to check is to check that U plus W forms direct sum in R3 or not. So that is, we have to check whether U intersection W is just 0 or not. Or we have to, or another way to check this is dimension of U intersection W is 0 or not. So we know that dimension of u plus w is dimension of u plus dimension of w minus dimension of u intersection w. So this is for any sum of vector spaces. And when dimension of u intersection w is 0, then dimension of u plus w becomes dimension of u plus dimension of w. And in this case, we say that u plus w forms direct sum. When we say that dimension of u intersection w is 0, that is, we mean that u intersection w is just this 0 element. So we first calculate what is dimension of u. So far, so this will imply C is equal to minus A minus B. Therefore, this A, B, C in U becomes so. So this is what we have. So what we are trying to do here is we have to check whether this u plus w are subspaces of R3, and we want to check whether u plus w forms direct sum of R3 or not. So what we will do is we will do that by calculating dimension of it. So what is difference between just sum of vector spaces and direct sum is that when we take this when we write u plus w, this is just vector space with a plus b, such that a and b both a is from u and b is from w. But when I say that u direct sum w, then this is subspace such that it is again has elements of the form a plus b, where a is from u and b is from w. But it has one more condition, that u intersection w is just 0 element. This is extra condition for direct sum. And we can check that using dimension formula which we have for addition of vector spaces. So dimension of u plus w is dimension of u plus dimension of w minus dimension of u intersection w. And when we have this dimension of u intersection w is equal to 0, that is u intersection w is just this 0 of vector space, then dimension of u plus w becomes dimension of u plus dimension of w, and in that case this addition of vector spaces become direct sum of vector spaces. So now what we are trying to do is we are just calculating dimension of u and dimension of dimension of w, and using, and then we will calculate dimension of u plus w and we will check what we get. Okay, and we say that it is, the question is that yeah, so we have to check whether R3 is direct sum of this u and w. So we also need to check that when, so dimension of R3 is 3. So when we say that R3 is the direct sum of these two vector spaces, in that case we also need to check that the dimension of u plus w is also equal to 3. So from this we have these two vector spaces. So u is generated by these two vectors, and let us check their linear independence. Suppose A, so this implies A is equal to 0, B is equal to 0. So anyway, we get that A and B both are 0. So therefore, this is basis of U. Therefore, dimension of U is 2. Similarly, we will calculate dimension of W. So W is ABC in R3, such that A plus 2B is equal to 0. And then we again try to write this A, B, and C in R3 such that A is equal to minus 2B. Okay, so this implies that A comma B comma C in R3 with A is minus 2B and A comma, so A is minus 2B, B and C such that B and C are in R. So note that here A is dependent on B, so we can get, so here we get rid of this variable A here. So this, if I want to write, this is minus 2, 1, 0 plus C into 0, 0, 1 such that B and C in R. So if I want to write this, then this is R minus 2, 1, 0 plus R 0, 0, 1. And yes, and you can again check that these two vectors are linearly independent, and we get dimension, this basis of W as minus 2, 1, 0, 0, 0, 1, and this dimension of W then becomes 2. And now we have to check dimension of U plus W. So note that dimension of U plus W is dimension of U plus dimension of W minus dimension of U intersection W. So this becomes dimension of U plus W is equal to 2 plus 2 minus dimension of U intersection W. So since U plus W is subspace of R3. Okay, so U plus W is a subspace of R3. So therefore dimension of U plus W must be less than equal to dimension of R3, which is 3. So therefore dimension of U plus W must be less than equal to 3. So using these two facts, we get that so this has to be less than equal to 3. So yeah, so we have this 2 plus 2, this dimension of U plus W, which is less than equal to 3. This is 2 plus 2 minus dimension of U intersection W. So this implies that dimension of U intersection W is greater than equal to this 4 minus 3, that is 1. So we get therefore dimension of U intersection W is greater than equal to 1. So from here itself we get that this U intersection W must not be zero space. And therefore we conclude that therefore this U plus W is not a direct sum of R3. So here what we are doing is we are not explicitly calculating or finding U intersection W, or we are not directly uh, calculating U intersection W and U plus W. But what we are doing is we are just calculating dimension of U and dimension of W, and using the dimension formula, that U plus W, this dimension formula here, we are just trying to calculate what is the possibility of dimension of U intersection W. So since both U and W had dimension 2 and 2, and since U plus W is subspace in R3, dimension of U plus W must be less than equal to 3. But since dimension of U plus W, so this RHS is less than equal to 3 and less than equal to 3, and sorry, this is less than equal to 3, and here what we were getting is 4 minus something, that entire thing must be less than equal to 3. So this minus must be at least of 1. I mean, what we are subtracting from this dimension U plus W must be at least number 1. So that's why we got this here. I mean, I hope you understand what I'm trying to say here. So this was my RHS and this was my LHS of this one. Or let me just use RHS and LHS, RHS1, LHS1. And we can see that this must be at least greater than equal to 1, so that this equation here makes sense, and this is proved fact. So they I mean, we can't say that it's okay that this does not happen. So yeah, so that's why we get that U plus W is not a direct sum. And now let's try to do that for the second part. I mean, if you want to calculate U intersection W explicitly, then what we have to do is, so see, I mean, if at all we have to find, if we want to find U intersection W, so let us do that as well. So if we want to find U intersection W directly, so what it means that A, B, C is in R3, U intersection W. This implies that A, B, C is in U, that is A plus B plus C is 0, and A B, C in W, that is A plus 2B is 0. So if my ABC, the vector is in both U and W, in that case, both the equation must satisfy simultaneously. And in that case, we have we calculate what are the possibilities of A, B, and C, and whatever we get will give us element from both U intersection W. Okay, so if we try to solve this simultaneously, we get, if we subtract, we get, we are subtracting, right? Yeah, from here we directly get, from second equation, we directly get A is equal to minus 2B. And if I subtract that in first equation, so if I call this first equation two equations, so 2 implies this. So if we substitute A is equal to minus 2B in 1, we get minus 2B plus B minus C is equal to 0. So we get minus B minus C is 0. So C becomes minus B in that case. I hope I'm correct. Minus B plus minus C. Oh, sorry, it is A plus B plus C is 0. So here, so yeah, C becomes B then. And therefore, we have these two conditions. A is equal to minus 2B, C is equal to B. And if I substitute that in this, so then for A, B, C in U intersection W, A must be, so what we get is U intersection W is A, B, C in R3 such that A plus B plus C is 0 and A minus A plus 2B is 0. And we got that if that has to happen, then we must have A to be minus 2B and C to be equal to B. And then we get minus 2B, B, and C is again B in R3 such that B in R. So this is just R minus 2, 1, 1. So this is the dimension of my, so this is my vector space U intersection W. Sorry. And we can directly from here see that dimension of U intersection W is indeed 1. So that's what we did. So here what we try to do is, first we uh, try to understand that U intersection W is not a direct sum, because if that was direct sum, then this vector space U intersection W will be just a zero space, but that's not happening here. Here we have U intersection W as this vector space here, which is not equal to 0 subspace. Okay, so that's it. And we already checked that this is not direct sum using the dimension equality as well. And so now the second part, we have to check that this, yeah, we have again now this U and W in R4, ABCD in R4, this vector ABCD in R4 such that A plus C is 0 and B plus D is 0, and W is ABCD in R4 such that A plus B is 0 and A plus D is 0. Okay, so if I want to again check what is, I now calculate dimension. So we will use the same method or tactics what we did for first part. So what we will do is we will calculate dimension for U, dimension of W, and we know that if this has to be direct sum of R4, so if U direct sum W is R4, then we know what formula it must satisfy, and we'll check whether that happens or not here. So we first calculate dimension of U. So U is my this space A, B, C, D in R4 such that this must happen, right? So A plus C is 0 and B plus D is 0. This implies that C must be A and D must be 0. So I'm not writing everything again and again. And so this will give me A, uh, B is again as it is, C is A and D is B in R4 such that A and B are in R. Okay, so this is just R. Okay, let me write it again. This is A1010 plus B0101 such that AB in R, and that is nothing but R1010 plus R0101. And then we can see that dimension of this U is 2 because we can, so you can check that these two vectors are linearly independent anyway, because if I take linear combination, the first entry itself will be the vector will be precisely this vector is equal to 0, 0, 0, 0, and that will give me A0, B0, and that's it. That will prove that these two vectors are linearly independent. And now my W is this vector space, vector subspace in R3. So ABCD in R4 such that A plus B is 0 and A plus D is 0. And now this implies that B is A and D is A. And now this becomes this vector space. A, now B is again A, C as it is, D is A in R3, so in R4, sorry, so that A and C are in R. So this will give me something of this kind. 1101 plus C into 0010. I'm just separating these two variables such that A and C are in R from real numbers. And this is just R1101 plus R0010. And you can again check that these two vector spaces are uh, linearly independent, because again, if I equate, so if I take A plus C is equal to 0, 0, 0, the basic linear combination, then we directly get A and C 0 for linear independence. So let me this is for linear independence. Yeah. So that's it. And again, so from here we get dimension of W as 2. So we have now dimension of U plus W is equal to dimension of U plus dimension of W plus dimension of U intersection W. So note that dimension of U plus W is less than equal to 4, since again, since U plus W is subspace of R4 and dimension of R4 is 4, we have this dimension of U plus W less than equal to 4. This implies that dimension of U plus dimension of W plus dimension of U intersection W is less than, sorry, minus dimension of U intersection W less than equal to 4. So that is 2 plus 2 minus dimension of U intersection W less than equal to 4. So dimension of U plus W, U intersection W is less than equal to 0 is what we are getting so far. But this is not enough. So see, when we write this statement here, this only, I mean, we still need to find what is dimension of U intersection W for this to make sense. That, I mean, from here, just concluding that the dimension of U intersection W will always be. So see, if the dimension is, yeah, so this is again the case. So if I want to conclude that something is not a direct sum, then using this formula, and if we are getting inequality of this kind, that where dimension of u plus w, sorry, u intersection w is greater than equal to 1, something of this sort, then we can directly say that it won't be direct sum. Okay, but in this case, this is not helping us. For example, in this case, in case of R3, we had dimension of U2, dimension of W2, and addition of them had dimension 4. So if the RHS, that dimension of U plus W needs to be less than equal to 4, that will give me that dimension of U plus W here must be at least 1 for this equality to make sense. Okay, and using this, we could directly conclude that U plus W do not form a direct sum of R3. But here, in this case, when we are trying to use this dimension formula to conclude whether the U plus W gives me direct sum of R4 or not, this is not helping, because what this gives me is dimension of um, U intersection W is greater than equal to 0. Okay, so that is anyway from here. So what this gives me is dimension of U intersection W is greater than equal to 0, or if I want to write it another way, it is dimension of U plus U intersection W is greater than equal to 0. But that is always true. Dimension of any vector space or any vector subspace is always greater than equal to 0. So this is not helping much. If we had something like this, that this is greater than equal to 1, dimension of U intersection W is greater than equal to 1, 2, or whatever number except 0, we could conclude that okay, this is not a direct sum. But since we got what we got is pretty obvious, and at this moment it is inconclusive whether uh, U plus W gives us direct sum or not. So to find that, to check that, we have to explicitly find now what U intersection W is. So what U intersection W is, so if I have A, B, C, D in R4 in U intersection W, this implies that A, B, C, and D in U, this implies that A, what we had earlier was A is, C is A and D is B. Where is it? Yeah. Or A plus C is 0, B plus D is 0. And if A, B, C, D in W, then we had A plus B 0 and A plus D 0. And if I want to solve these four equation at a time for, so this is AND, so that ABCD vector is in both U and W. And if I want to find dimension of both of these, all of this, then I have this A. From here, A plus B is equal to 0 implies A. So see, from here I have B is equal to minus A and D is equal to minus A. And so if that is the case, so from here I get, if I substitute minus A here, so minus A plus D is equal to 0, this will give me D is equal to A. So here I have D is equal to minus A. So let me name this 1, 2, 3, and 4. So 1 implies this, sorry, 3 implies this, 4 implies this, and 3 in 2 implies this, and then now this and this collectively gives me D is equal to 0. And because D is also plus A and minus A, so D is equal to 0. And the moment I have D is equal to 0, this will give me A also 0. And if A is 0, I get C is 0 from 1. A is equal to 0, so this implies C is 0. This is from 1. And I also get that B is also 0 from, from 3. So ABCD, all 4 are 0. So therefore, A is equal to B is equal to C is equal to D is equal to 0. So this implies that only possible vector which is in U intersection W is 0. Therefore, only this vector belongs to U intersection W. And therefore, dimension of U intersection W is 0. And we get dimension of U plus W is equal to 4. Because which is okay, dimension of U plus dimension of W, which is 2 plus 2. Therefore, dimension of U plus W is 4. And now we can conclude that it is indeed direct sum of both U and W. So therefore, we can say that R4 is U direct sum W. So any doubts here? What we are doing? What we were trying to do is just calculate. I mean, just to check whether that whether R3 and R4 are direct sum of given vector subspaces of R3 and R4 or not. So what we did was, in first case, we used dimension formula, and we got that if direction formula satisfies, then in that case dimension of U intersection W will be greater than equal to 1, and we could conclude that U plus W is not what we can say is not, it cannot form direct sum. But in second case, when we tried to use dimension formula, we got that dimension of U intersection W less than equal greater than equal to 0. But that is true for any vector space, so we are not getting any special information about U intersection W. So what we did, we tried to explicitly calculate what U intersection W is, and we got that U intersection W is just singleton 0. That is okay. Let me write it here explicitly. U intersection W is just this element 0 0 0 0. And then we could and now that we have that, we get this dimension of U plus W is dimension of U plus dimension of W, and therefore dimension of U plus W becomes 4. Any doubts here? So I hope you know the difference between this. So this is just U plus W such that U in U and V in W. Sorry, yeah, W in W. And this is also U plus W such that U is in U and W is in W. And U intersection W is singleton. That's it. This is the only difference between these two. This is normal vector sum and this is direct sum. The only difference, yeah, that's it. And so now we'll go to next question if there are no doubts. So let x be 1 1 0 0, y be 1 0 1 0, and z be 0 1 0 1, and w is this 0 0 1 1. And they said that let u is rx plus ry, and w is, they are defining u and w like this. using the vectors x, y, z, w, and this is rz plus rw, and we have to find u plus w, u intersection w, and dimension of u plus w and dimension of u intersection w. So note that here, when we want to calculate dimension of u plus w and u intersection w, it is enough to calculate dimension of one of them because we have the dimension equality. Okay, so let us first see what the way we have this this u and w defined, uh, it is clear. So if these two vectors x and y and z and w are linearly independent, in that case dimension of u and dimension of w is pretty explicit, that it is 2 and 2 each respectively. So so note that x, y are linearly independent. Similarly, I mean, you can check if you are not convinced. Z and W are linearly independent. Okay, and so therefore, this dimension of U is 2 and dimension of W is 2. But anyway, in the question, we are explicitly asked to find what is U plus W is. So U plus W is what? U plus W is addition of both this U and W. So this is U plus W, where U is in U and W is in W. So when we say this means how elements of U, how elements of U look like. So elements of U are of this form: 1, 1, 0, 0. So this, let us write first how elements of U look like. So U is addition of these two vectors, right? Rx plus Ry. Rx plus Ry. So this is A. X is, I'm correct, X is 1, 0, 1, 1, 0, 0 plus B 1, 0, 1, 0 such that A comma B in R. So this is element of this kind. A, B, oh yeah, no, so, oh, A plus B comma B comma 0 such that A, B are in R. And now W is RZ plus RW. So this is C 0101 plus D 0011 such that C and D are in R, and this becomes 0 comma C comma D comma C plus D such that C comma D are in R. Okay, so U plus W now becomes addition of these two. So any element in U, see, this is U plus W such that U in U and W in W. But how elements of U and W look like? So elements of U are of this form: A plus B, comma B, comma 0 plus elements of W of this form: C plus D such that C, okay. And then this A, B, C and D are in R. This is what we have. And if I separate all these vectors, I get that this is, again, we go back to just addition of those four elements. 1 1 1 0 0 1 1 0 0. B is 1 0 1 0 plus C into 0 1 0 1 plus D into 0 0 1 1, such that this A, B, C, and D are in R. So what we have to check is whether they are linearly independent or not, whether all these four vectors are linearly independent. So what we know that U plus W is generated by these four vectors. And now to conclude that that U plus W, so what we have to do is, when we are asked this, find U plus W and find U intersection W, what we need to do is we need to give explicit basis, at least one basis for this vector spaces. So what we will do is we will try to find the basis for this. And how to do that? We have to find the possibilities for this ABCD. So if I combine these from this second part, I get this A plus B, comma A plus C, comma B plus D, comma C plus D, such that A, comma B, comma C, D are in R. And to conclude that, so any element in U plus W looks like this. Okay. And if I want to check whether this, so to check linear independence, to check linear independence of of this X, Y, Z, W, what we do is we already have this linear combination and we have to just equate it with respect to 0, 0. If there is any doubt why we are doing this, please stop me and ask. So this gives me A plus B is equal to 0, A plus C is equal to 0, B plus D is equal to 0, and C plus D is equal to 0. So A plus B is equal to 0 means A is equal to minus B, and here I get this gives me D is equal to minus B, or no, yeah, B is equal to D minus D, C is equal to minus D, and A is equal to minus B. So minus B, B is minus D, so it becomes minus of minus D, so it becomes D. And the moment I have A is equal to D, so from 2, so this implies A plus C is equal to 0, then D plus C is equal to 0, and this will give me C is anyway minus D from here. So see what I have, A is equal to D, B is equal to minus D, and C is equal to minus D. So that's it, we are done. So this, and nowhere we are getting any equation where D is vanishing. So we are not getting some condition of this kind, that B is equal to minus D and B is equal to D, something like that. If this something like this had happened, then this would imply that B is equal to 0, and that will give me D is also 0. But nothing like that is happening. When we have this, then from here also we are getting C is equal to minus D from A is equal to D equation. So what I have at the end is A is equal to D, B is equal to minus D, C is equal to minus D, where D is in R. So this U plus W, oh, sorry. So our thing is, oh, are we making any mistakes here?
So they are not forming a linearly independence, ma'am.
Yes, they are not forming linearly independent. That is
Yes.
okay. But what I'm saying is that using this, what we are getting, that this A, B, C, so this becomes U, okay. So when I am saying that this is equal to 0 and I'm getting something, so these are not linearly independent, that is okay. But still we need to find dimension of these vector spaces, right? Right now what I have is
Yes,
something
ma'am.
like, yeah, what I have is D minus T and D, something like this. And this gives me that, okay. So this implies that this X, Y, Z, W are not linearly independent. So we have to still find dimension of U plus W. So dimension of U plus W. So what we can do is,
So definitely not 4.
yes, definitely not 4.
Yes,
But we
ma'am.
still need to find what exactly it is, right?
Yes, ma'am.
So U plus W is span of X, Y, that is. So if I write it in the matrix form, matrix of this X, Y, Z, W, this is X, Y, Z, W. Each is a vector 1, 1, 0, 0, 1, 0, 1, 0, and 1, 0, 1, 0, and 0, 0, 1, 1. So this is my X, this is Y, this is Z and W. And if I try to convert this into row echelon form, then one of them would vanish. So dimension of U plus W is number of non-zero rows in row echelon form of this matrix, right? So if I want to do that, what I will do is I want to make this first entry 0. So I will get 0, 0, sorry, 0 minus 1, 1, 0, 0, sorry, minus 1, 1, 0, and 0, 0, 1, 1. And then I'm subtracting these two here, 1, 1, 0, 0, and 0 minus 1, 1, 0. And I will just get this. Okay, so this, wait, what I'm writing is it? So this is it. And then if I swap, I get 1, 0, 0, 0 minus 1, 1, 0, and 0, 0, 1, 1. And that's it. And now we can't further simplify anything, right? I mean, that's it. Uh, this is in row echelon form. I mean, just multiply this second row by minus 1, and we will get this 1, 1, 0, 0, 0, 1, minus 1, 0, and 0, 0, 1, 1. And therefore, dimension of this U plus W becomes 3. And but which one of these three generate the fourth one? So can we write 3 as a linear? So if I can write this as a linear combination of, so this is 1, 1, 0, 0 plus 1, 0, 1, 0, 0, 1. So if I want to write, so let us try to write this 0, 0, 1, 1 as sum A 1, 0, 1, 0. Why we are doing this? Because we are explicitly asked to calculate this vector space U and W. Okay, if we were asked to calculate only this dimension, then we are already done. Then dimension of U plus W will be something, and dimension of U intersection. So we already got the dimension of U plus W is anyway, is 3. And then using the formula, the dimension of, so using dimension formula, we can directly conclude the dimension of this will be 1 because dimension of U and W is 2. But we are also asked to give explicit expression of what is U plus W is. So to do that, so it is anyway, we know that U plus W is linear combination of these 4. But if I can, and we know the dimension is 3. So if I can express one of these vectors in the linear combination of other 3, then I'm done. So that's what we are doing here, so that we can, so B is what? 0, 0, 1, 1. So did I make any mistake here? Sorry. I think I made a mistake here. Oh, sorry. What is, oops, this was 0, 1, 0, 1. Sorry. This is not exact. This is 0, 1, 0, 1. And now I get, that's it. And I still have this. So sorry, this was not correct. I repeated the second and third row. And now I will just swap these two. 1, 1, 0, 0, 0, 1, 0, 0, 0.
Uh, Can you just write this R2 minus R1, which row to which row you are subtracting?
Okay. I will do that. Yeah. This is R2 minus R1. And this is, I'm doing just R3 swap R2. And now I'm doing R3 plus R2. So this is 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And this is 0, 0, 1, 1. And now from here, this is not correct symbol. And now I'm doing here R4 minus R3. And now I'm getting this 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 0, 0, 0, 0. And R4 here was as it is. And we could subtract R4. I mean, we could make R4 0 just by doing the combinations from R1, R2, R3. So we can write this, that so R4 is equal to what is happening in R3 plus R2. R4 was R4 minus R3. So 0 is equal to R4 minus R3. And R4 is, and R3 was R3 plus R2. I don't know what I'm doing, but I'm just trying to do something. And this was R2 was R2 minus R1. And this gave me 0. So I get R4 is equal to R2 plus R3 minus R1. Is it true? We also swapped, right? 2 and 3. So if that is the case, doesn't matter. But is this true? R2 plus R3. R2 plus R3 is this 1, 1, 1, 1 minus R1. Yeah, that's correct. addition of these two will give me entire 1 minus R1. That's true actually. So R4. So that is Z is equal to, sorry, W is equal to X plus Y minus, sorry, Y plus W minus Z. Or W is equal to Z plus Y minus X. Yeah, this is what we have. Okay, so therefore, dimension of U plus W is 3, and dimension.
How did you get this 0 is equal to R4 minus R3?
This is, I'm just tracing what is happening to R4. So see, when we got R4 is equal to 0, it means R4 is a linear combination of other things. And what become is R4 become R3. Something is 0 means I could write this vector as a linear combination of other three so that I could subtract it. So this R3, the way I got, is actually R4. And how I got R3? R3 I got when I did R2 minus R1, and then I did R3 plus R2. This is really bad.
Oh, okay. I mean, R4 minus R3 or anything we can write.
Yes.
R3 minus R4 is equal to 0 also we can write it.
Yes, this is R4 is equal to R3 minus R4, right? So that's what I did. But this is I got as 0 row. So 0th row, this R4 is what? R4 minus R3. But here I swapped, what I did, this R3 here is R3 plus R2. So this I just wrote R3 plus R2, and then I am swapping R2, R3. But that is not making any check. That is just, I'm writing R2 plus R3. And then R2 is my R1 minus R2 minus R1. So I'm just substituting. So what I'm doing is this here is this here is this. And then this swapping is not helping. It is just, but the addition is commutative anyway in vector space. So that is not helping much. So this step. And then what I'm doing is this.
Okay.
R2 plus R1. And now that R2 plus R1 is here.
Fine.
Yeah. So that was just to trace how this R4 is linear combination. So when I'm getting this, I'm taking this R4 on the LHS and I'm getting this. But what this R4, R3, R2, R1 represented? This was explicitly X, Y, Z, and W. So I could write W in terms of X, Y, Z now. And that's why dimension of U plus W is 3, and U plus W is generated by, it is Rx plus Ry plus Rw, sorry, Rz. So it is three-dimensional vector space. And now they are asking dimension of U intersection W. So using dimension formula, we can directly have this, right? Dimension of U, dimension of W minus dimension of U intersection W. So this we know is 3. Dimension of U plus U is 2, dimension of W is 2, minus this dimension of U intersection W. And this will give me dimension of U intersection W as 1. Sorry. So we know that intersection will be one-dimensional vector space. Now we explicitly need to calculate what this U intersection W will be. So as we did earlier, we have to do the same thing. That U intersection W will be, so this, yeah. So intersection W, what was that? Yeah, this one. So let me just explicitly write what is UA and W so that we won't get confused. Okay, U is just span of 1, 1, 0, 0 and 1, 0, 1, 0. and W is span of, I think it is 0, 1, 0, 1 and 0, 0, 1, 1. Okay, and now I want to find what is U intersection W. That is something, so U is AB. Yeah, A plus B, comma A, comma B, comma 0, such that AB in R, and W is C, comma C, comma D, sorry, 0, comma C plus D, such that C plus D is in R. Sorry, C, comma D is in R. And if I'm saying that U belongs to some element V belongs to U intersection W, this implies that it belongs to both, right? That if I call it not X, Y, Z, W, what to call it? Can someone give me some names? Let us call this PQRS belongs to U. This implies that S is 0, right? And S is 0, and that's it. And from here I will get S is 0, and wait, here I have PQRS belongs to U. So this implies this is of the form P plus Q, comma Q, comma R, and S with of, I'm just trying to do something, P, Q, R and R plus S. So this implies that, but this first entry is 0 if it is in W. So this gives P plus Q is 0. This gives R plus S is equal to 0. And that's it. And if that is happening,
Yeah, this step
yeah.
is clear. I mean, it's fine. We just map PQRS from the above. We wrote it P plus Q, comma Q, comma R, comma 0. Then how come this P plus Q is equal to 0? We took it here.
Because see, first entry, okay, what we are doing is, this also belongs to W, right?
Yes.
Yes. If this belongs to W, so
Okay, in terms of the Q, we wrote it.
yes, this belongs to W implies
P plus Q will be 0.
yes, this becomes 0, comma Q, comma R, comma Q
Q.
plus R. So if I equate, this implies P plus Q is 0, and
Q plus R is equal to 0.
yeah, Q plus R is equal to 0. So this implies P is equal to, no, Q, no, yeah, P is equal to Q minus Q and R is equal to minus Q.
So
And both the first entries are 0, right? Or is there any error? No, there is some error. The way we have given the names is not correct, actually. If, forget this, if this is the case, A plus B, comma A, comma B, comma 0 is equal to 0, comma C, comma D, comma C plus D. This will imply A plus B is equal to 0. C plus D is equal to 0. A is C, D is B is D. And this will give me A is minus B and C is minus D. Right? I want the dimension to be 1, right? Yeah, so we are done, right? The first entry is anyway 0. So we have to see if something is in the intersection, these imply it will be of this form 0, some PQ, 0, such that P and Q satisfy certain condition. But here we have AB, so this will basically 1 and minus 1. So this will be of this form 0, 1, minus 1,
0,
0.
A minus A, 0, right, ma'am?
Yes, exactly. Because, yeah, A is,
0, comma, A, comma,
yeah,
minus A,
here
comma,
C is,
0. Yes,
yes, this A is equal to minus B
minus
means,
B.
yeah, so this becomes this 0, A becomes
A,
minus B, A and 0, sorry, B 0. And here C is minus
okay.
D means similar thing, minus D, D 0. We are equating both the things. Anyway, and once I have this anyway becomes 0 and the last term anyway becomes 0. C plus D because C is minus D. I hope that's okay and understandable. Yeah, that's what we did here. So if we want to write something, if or let this be as it is, what we are doing is if something is in, so if U belongs to U intersection W, then U is some AX plus BY and it is some CZ plus DW. XYZW is given. So this will give me, yeah, that's what we did, right? This is A plus B, comma A, comma B, comma 0. This is because in the intersection, right? So U is some AX plus BY and U is also some CZ plus DW. And this was again 0, A, sorry, C, comma D, comma C plus D. So first equation we get is A plus B is equal to 0. Second equation we get C is equal to A is equal to C. Third equation we get B is equal to D. And final equation we get 0 is equal to C plus D. So this will give me B is equal to minus A and B is equal to minus A. This is C is equal to A. And once I have C is equal to A, so I have A plus D is equal to 0. This will give me D is equal to minus A. So that's it. I got B in terms of A, C in terms of A, and D in terms of A. And here again, B is equal to D is happening because B is equal to minus A. And yeah, I mean, B is also minus A, D is also minus A. So that's there. So if I substitute A plus B, then what I get here? This X minus Y is equal to C is equal to A. So AX plus BY is equal to AZ plus D is minus AW. If I substitute this here, what I get? B is minus A. So A minus A comma A minus A0, and this becomes C is anyway A. So 0 comma A comma D is minus A comma anyway addition of this is 0. So ultimately we get this A minus A becomes 0, A minus A and 0. So this is A into 0, 1 minus 1, 0. And this is element in U. So yeah, we finally got the expression. I hope this is clear now. Sorry for all that confusion. But is this okay now? So once I have this, I just substituted back in here and we got similar equation that U has this form. The first one, A plus B, A plus B became 0 and C plus D also became 0 here because C was A and D was minus A. So the last two term which we anyway got 0 here became as it is, and then A was minus B and C was again minus D, and it followed in short. That's what we tried to do here. This is explicit. I mean, what system of equation we calculated in order to get hold of this ABCD is this. And this is what we got, that everything is dependent on A, and ultimately we got this expression. Yes, so therefore, no, this is U intersection W. So therefore, U intersection W is span of this 0, 1, minus 1, 0, and dimension of U intersection W is anyway 1, as we anyway calculated from the formula here. So yes, any doubts here? So what made us spend that much time was we could not find this system of equations here earlier quickly. Okay, and that we could do when we actually wrote that what equality we need to follow here. That Ax plus By, I need it to be equal to Cz plus Dw. For some, so this is the system now. Ax plus By minus Cz minus Dw is equal to 0, 0, 0, 0. And now we are trying to find what this ABCD will be in that case. Uh, is that okay? I hope that's fine now. We'll move to next question now. We have this is question, I think, third, whatever. Yeah, and yes, so this is question again in third. Yeah, suppose we have this. Suppose that U and W are subspaces of R13 with dimension R of U is 7 and dimension R of W is 8, then we have to find, I'm directly writing the largest, possible dimension of U intersection W. Second is the smallest. So when you are asked to calculate such questions where we are asked to calculate the largest and smallest of the given dimension, what we can do is we can take the worst possible and the best possible dimension, and we can check whether that's possible or not. And what that worst and best possible is, that we will see what we mean by that. U plus W, and fourth is the smallest possible. Okay, so yes. So we are asked what is largest possible dimension of U intersection W. So see, U and W are are subspaces of R13, and dimension of U is 7, dimension of W is 8. So see, what we have is dimension of U plus W is dimension of U plus dimension of W minus dimension of U intersection W, right? So this dimension of U plus W is largest when? Sorry, we want largest possible dimension of U intersection W. So what will be the maximum dimension of U plus W? See,
when they are totally dependent.
yes, I mean one is contained in other, right? I mean, see, note that dimension of U intersection W,
If it is 0,
we want largest possible. Largest for this first one, largest for U intersection W, dimension of U intersection W. So see, dimension of U intersection W is contained in both U, and U intersection W is contained in W, right? So dimension of U is less than equal to dimension of U intersection W is less than equal to dimension of U, and dimension of U intersection W is less than equal to dimension of W. And if that is happening, this implies that dimension of U intersection W is less than equal to dimension of minimum, whatever is the minimum, right? Because we are doing less than equal to. So this is minimum of dimension of U and dimension of W. So what is the minimum of them? Here dimension of U is 7, and if I'm correct, yeah, and dimension of W is 8. So dimension of U intersection W is therefore less than equal to 7. So maximum possible dimension is 7. There is no other possible value of U intersection W. Is this okay? We just use this basic fact that intersection is always contained in the original subspace. Yes. So this gives me something that it will always be maximum. And now I'm asked to calculate what is the smallest possible dimension of U intersection W. So now we can make use of this. See, I mean, smallest possible, we can always say that this is always greater than equal to.
Have you done the first one?
Yes, we are done with first one.
The largest possible dimension of U and
Yes, this is the only largest, right? Dimension of U intersection W is always less than equal to 7. So the largest possible value it can ever take is 7. There is
7.
nothing yeah.
Okay,
Because
right.
see, dimension of U intersection W is contained in U. So dimension of U intersection W will be less than equal to U. We know that.
Right.
And similarly, dimension of U intersection W is in U intersection W is contained in W. So dimension of U intersection W will be also less than dimension of W.
Minimum of that.
Yes. Then if I want something to be less than both the things, then it must be less than minimum of those two things. And in this case, dimension of U is 7 and dimension of W is 8. So it is minimum of 7 and 8. So that is 7. So the maximum possible value it can take is 7 because dimension of U intersection W is always less than equal to 7.
Right.
Yes. So now we are going for the second where we have to find the smallest possible value. So note that smallest possible value for any dimension is always 0. But is that the case? I mean, if in general anything is greater than equal to 0, but is that really possible? So I hope you. So this we know this dimension of U plus W is dimension of U plus dimension of W plus minus dimension of U intersection W. So this is dimension of U plus W. So this can take maximum value 7 plus 8 minus dimension of U intersection W. So this is 15 minus dimension of U intersection W. And this is, since this is 15 minus dimension of U intersection W. And note that U plus W is subspace of R13. So this implies dimension of U plus W will be less than equal to 13. Right? So this will give me that dimension of U plus W is equal to 15 minus dimension of U intersection W is less than equal to 13. So this implies that 2 is less than equal to dimension of U intersection W. So the the smallest possible
2.
in this case is 2. The intersection will have at least 2 elements in them. Is that okay?
Right.
Yes. And now this part. Now we will do the similar kind of thing for addition. So the largest possible for
Can you
yes, sir.
just say a small difference between plus and union here? I just miss it. I mean, how
Yeah,
plus
plus
union is? Plus is simple plus without intersection, huh?
yes, yes, yes.
Oh,
So
okay.
yeah, U plus W. See, U plus W is just U plus W where U is in U and W is in W. And when I say that U plus W is direct sum, then it means that it is U plus W again, U in U and W in W. And this U intersection W is just zero set. So
Okay.
and in this case also, dimension of U direct sum W is always dimension of U plus dimension of W. Because intersection is 0. So dimension of intersection is always 0. So using the formula, we can always get this. And U union W is just subspace generated by, it is span of U and W, if I write it correctly. This is also actually, see, U union W when I write, then it is just basic union. This does not really make sense. This is just a set contained in V, but this is subspace. And we know that U plus W is subspace generated by this U union W.
So U plus W will always be smaller than or at max U plus U union W.
No, it's other way around. U union W will all, sorry.
Now
What?
U plus W will be always U plus W is smaller than or at most U plus U
No,
union W.
this will be there, right? U union W will be contained in U plus W. Because see, I can always have this U plus 0 in U plus W and 0 plus W in U plus W, right? That is just union. So union means this set is just elements such that A in U or A in W, right? V in U and V in W. So this V I can always write V plus 0 and 0 plus V, right? Union will always be inside sum, and sum is something
Actually,
bigger. For example,
the
if
sum
I
is
take,
something bigger. Okay.
yeah, because see, if we take x and y axis, my U is x axis and y is this, then U union W is just this line. Red is, if my U, let me write this, U is x axis and W is y axis, then U union W is just this red line, these two red lines. But
Okay.
if I want to take this whole U plus W, then this is entire R2. It contains everything. U
Achha.
plus W is whole R2.
Right.
Everything. Yeah.
Okay.
So U plus W is something bigger. So U plus W is indeed, it is span of this U union W, or we can say that it is generated by U union W.
Right.
So
Right.
it
Okay.
is all the possible linear combination of both the elements
Both the
from U
elements.
and W.
Okay. Okay. Okay.
So that's why when I said this, that this is just the set. This does it. This is not closed under addition or anything. This is just basic union of two subspaces. And
U
if
plus
you
W
remember,
will be complete closure, na?
yes, this will be, sorry, sir,
U plus W will include all the points.
all the points. Yeah, the closure means under addition.
Yes, under
Yes,
addition, yes.
yes. And if you remember, we did that. This, if U plus W is U union W, then either U is contained in W or W is contained in U. We proved this in the, like, I think in the first or second
Okay.
lecture, if you remember. I mean, that in back then also I said that this is just a set. When someone write this, it means that this U union W is forming. This is just a set, and this is a subspace. So when they are writing this, they means that U plus W now in this case is forming a subspace.
Okay.
Yeah. So this equation even has some meaning. What is trying to say? This is not, so this is subspace and this is U union W, it just said. And when we write this, it means that this U union W is now forming a subspace. And when that happens, one of these condition holds, that U is either contained in W or W is contained in U. Is that okay?
Yeah, that is okay. Fine, fine.
Yeah, yeah. So now we have to do the largest and smallest possible dimension of U plus W. So let us try to do that. And now we have this. Now note that this uh, uh, how to do this. This is, note the dimension of U plus W is dimension of U plus dimension of W minus dimension of U intersection W. So for this to happen, for this, okay, so for this to become maximum, uh, this part must be smallest as possible, because this is anyway fixed. This is 7 and this is 8. So these numbers are fixed. So if I want to make this as something maximum, then this must be smallest. And the smallest of U intersection W we just calculated, it is 2. Okay, so therefore, the smallest possible value of dimension U intersection W is 2 from part B, from second part. So therefore, dimension of U plus W is 7 plus 8 is greater than equal to. So see, 2 is now, see, dimension of U intersection W is greater than equal to 2. So this I want smallest. So minus will be less than equal to. So this minus 2 is less than equal to, yeah. Yeah, this is correct. Minus dimension of U plus W. And this will be less than equal to 7 plus 8 minus 2. And this is 13. Because this is less than equal to minus 2. I hope that's okay. And similarly for fourth one.
Intuitively
This,
also, if U and W are the subspace of R13, then it cannot go beyond 13.
yes, exactly. That is also, I mean, that's also true. I mean, the maximum possible value. See, I mean, maximum possible value it could take. So in general, the maximum possible value for maximum of this will be, see, it could be, yes, this is, in let me keep it as it is. So this maximum of dimension of this U plus W will be minimum of this, right? Dimension this 7 plus 8, comma dimension of V, right? It has to be minimum between these two.
Right.
Yeah. Because see, it will always be less than equal to dimension of the vector space. And it will maximum can be addition of dimension of these two vector spaces. Does not matter what the intersection is. So in that case, this is only these two possible cases. So maximum of, let me write, the maximum of dimension of U plus W is minimum between dimension of U plus dimension of W, comma, dimension of V, the original vector space. Because see, if the addition was, for example, U was of dimension 3 and W was of dimension 5, for example, then the maximum dimension of U plus W would be 8. And in that case, this 13 would not play much role. That's why it is minimum between these two things and the original dimension. For example, if it is exceeding the dimension of original vector space V, that in that case it is minimum, it is lower than V. And if the addition is lesser than the original dimension of original vector space, then it will be equal to this thing, addition of those given two vector spaces.
Right.
Yeah. And now the fourth part. See, here we could do this because we had hold of minus of.
No, upper limit anyway is defined is by dimension
Yes.
V.
Yeah, this 13 here Yeah, this 2, how it is getting is actually from the dimension being 13, because that's what we used here actually.
Yeah.
Yeah, I mean, we are not doing anything extra by doing this here. I mean, this -2 which we got here was actually because of dimension of V is 13.
Okay.
Yeah. And now the smallest possible for these two things. Yeah, smallest possible for dimension of U plus W. And what it will be. See, U plus W contains U, and U plus W also contains W. Right. So if that is the case, then dimension of U plus W is less than equal to dimension of U, and this implies dimension of U plus W is less than equal to dimension of W. So then this implies that dimension of U plus W will be greater than equal to minimum of these two, right? Or maximum. Oh, sorry. It must be greater than equal to both of them. So it will be maximum. So in this case, therefore, dimension of U plus W will be greater than equal to maximum of 7 and 8 is 8. Because it has to be greater than equal to both of this. This is and. So it has to be greater than maximum of both. Yeah. So that's it. And then next question. Yeah, we have that. Yeah, we will try to do this question. That the sum of subspaces, this I think question 4, the sum of subspaces U1, Un of V is a direct sum if and only if, okay, if and only if this U1 to UI intersection UI, oh, this is not just comma, this is plus UI intersection UI plus 1 is 0 for all 1 for all I is equal to 1 to n minus 1. This is what we want to prove. That's the question, right? Yeah. The subspace sum of subspaces of V is a direct sum. So direct sum means intersection of uh, all this is 0. So when we have this is also called as mutual intersection between any of these two is zero. That's what it is called in general when we have multiple direct sum. So what we need to prove is that V is U1 plus U2 plus UN if and only if this happens, that U1 plus UI. Now when we are writing this plus, sorry, this is normal addition. This is not the direct sum plus. So we are, yeah, so this is just basic addition. So what they are saying is when we add I many and then intersect with the I plus 1, I mean this ui plus 1, then it will be 0. This 0 is 0 set. Okay, so let us try to understand. Okay, so I hope this is okay. Okay, so, and when we say this means that if u1 plus u2 plus un is 0, this imply ui is 0 for all I in. This is what it means. The direct sum. In direct sum, we know that u intersection w is 0. That means no u plus w becomes 0 other than u and w both being 0. I hope you understand what that means, right? That u intersection w is a 0 in u plus w. It means that this is just u plus w and this is happening. So this is just normal basic u plus w, but in this my case intersection is 0. So if there is any u in u and u in w, then that just 0, because if something non-zero belongs to u intersection w, these imply that u is in u and that u same belongs to w, and then their addition would, I mean, that then we can get non-zero elements in both the sets, which when I add, I will have some non-zero linear combination coming from both u and w. I hope you understand what I'm trying to say here. This u plus this minus u will give me 0. And that is something which I don't want here with u non-zero. Okay, something like this would happen. Whatever. So please try to understand what I'm saying here, okay? So when we write direct sum, it also means that if there is some vector belonging to this direct sum, then it can be written as unique linear combination of this u1 to ui's. No other such linear combination is possible for that. So we will use that fact here to prove. So forward direction is that we are assuming, so given that this u1 plus un is a direct sum. So, and we have to show that u1 plus ui intersection this ui plus 1 is 0 for all I between 1 to n minus 1. Okay, so let some u belongs to this intersection u1 plus ui intersection ui plus 1. So this implies that u is so this u is in ui plus 1. So this implies that this u is, let me just not take u here, let us take v. So suppose this element v belongs to this intersection. So this v belongs to this ui plus 1 coordinate. So this implies this v is some ui plus 1 for ui plus 1 belongs to this, right? And similarly, this v is also in u1 plus ui. So this implies that this v is u1 plus ui, where this ui belongs to capital Ui. Right? So this will give me u1 plus ui is equal to ui plus 1, right? Because both are expressions of u in these respective vector spaces. So this will give me this u1 plus ui minus ui plus 1 is equal to 0, right? With each ui here belongs to capital Ui for all 1 less than equal to I less than equal to this I and for now we have this much information. And if I try to write this as this linear combination ui plus minus 1 into ui plus 1 plus 0 plus 0. So this 0, when I'm writing here, this is ui plus 2. This 0 is in un. And this is a expression of a 0 which is other than what we say. So this implies that 0 is not uniquely expressed as sum of u1 to elements from u1 to un. Okay, so that's why. I mean, when we say something is direct sum, the expression becomes unique. And that's what is not happening in this case. Okay, there are elements which are there in the intersection of these subspaces. Is this okay? So that's what I'm saying. So if this is this, so therefore, as sum is direct sum, the expression of 0 must be unique. And one expression for 0 is taking 0 from each ui, and then it is 0 plus 0 plus 0 is equal to 0. And but now if this v is non-zero here, then we have other expression this u1 plus ui plus this minus ui plus 1 plus 0 from everything. And this is 0. And since I assumed non-zero, this is non-zero, and therefore this is non-zero linear combination of 0. So this no longer becomes direct sum. This contradicts the fact that u1 plus un is direct sum. Okay, so therefore our assumption that there exists some non-zero element v in the intersection is false. Therefore the intersection is 0. That's what we wanted to prove. Therefore our supposition is wrong. And this u1 plus ui intersection ui plus 1 is 0. Okay, I hope this is okay. Now the converse part we will prove. And then the converse part is we are given that here given that u1 plus ui intersection ui plus 1 is 0 for all 1 less than equal to I less than equal to I n plus n minus 1. And we have to show that this u1 up to un is direct sum. That is, if u1 plus un is 0, where this ui belongs to ui, then this each ui is 0. That's what we need to prove to show that this u1 to un is a direct sum. So what we will do is we will prove it by induction. So base case n is equal to 1. So proof by induction. So n is equal to 1 case. So what we have is u1 plus u2 is 0. Sorry, u1 intersection u2 is 0. And in that case, if that is the case, then anyway u1 plus u2 is the direct sum, because that's what we want, something to be direct sum. This implies u1 plus u2 is direct sum by definition. Okay, and now base case n is equal to 2. Oh, not n is equal to 1 means this is u1 and u2, right?
In case of n is equal to 1, it will be only u1, na?
Is it? Yeah. 1, yeah, this becomes 0, right? This is like 1 less than equal to I less than equal to 0. So yeah, this is only u1. So n is equal to 1 is actually what we say. It does not make any sense. I mean, here it is vacuously true because we do not have two vector spaces to talk about direct sum. Okay, so if n is equal to 1, then the sum is just 1. u1, and so no intersection condition. So this is vacuously true because there is nothing to check. Okay, so now the case n is equal to 2. Now I have this u1 intersection. Yeah, now it is correct. Now I have u1 plus u2 here, and this is sorry. Now I have u1 intersection u2 is 0. And this anyway imply that u1 plus u2 is direct sum, because that's what we need. Right, to show that u1 plus u2 is direct sum, all we need to show is that u intersection 0, u1 intersection u2 is 0, but that's what hypothesis is for n is equal to 2 case. So now suppose assume for n is equal to k, and we prove for, so this is trivial. So we prove for n is equal to k plus 1. Okay, so suppose I have u1 plus u2 plus uk is equal uk plus uk plus 1 is equal to. So when I say this, I need to show that this u1 up to uk plus 1 is direct sum. So I'm assuming k plus 1 sum here, and I'm taking this is equal to 0. So this will imply that u1 plus uk is equal to minus of uk plus 1. Okay, and then this will imply that this element u1 plus uk, this belongs to this u1 plus uk, and this minus uk plus 1, this belongs to uk plus 1. So this imply, and this is equal to u1 plus, this is also equal to. So this implies that this element u1 plus uk belongs to both u1 to uk intersection uk plus 1. And this is my, so this becomes n is equal to k case, right? So then by induction hypothesis, u1 plus uk intersection this uk plus 1 is 0, and this will imply that this element u1 plus uk is 0, and this is my anyway minus uk minus 1, so this will imply this minus uk plus 1 is also 0, because this is equal to this. So oh wait, that is okay, this is 0 and uk plus 1 is 0, that is okay. But now again I need to show that each uki is 0, ui is 0. But now since this is 0 and we are in induction case, this u1 to uk belongs to this, right? And we know that u1 plus uk is direct sum. So this implies that each ui is 0. From induction step we got here that u1 plus uk intersection uk plus 1 is 0. And from there we have this u1 plus uk becomes a 0 and uk plus 1 becomes 0 using this equation. But we only have this summation as a 0, but we want each of this ui to be 0. We need to prove that. Where is it? I did not write that. That is okay. Let me just write that explicitly. Assume for n is equal to k, and this, and direct sum, that is if u1 plus uk plus 1 is 0 for ui belongs to ui, then each ui is 0. This is what I need to prove. Or this is what we are trying to prove for all 1 less than equal to I less than equal to k plus 1. And now I got k plus 1 as a 0. And since this u1 plus uk is falling under the induction hypothesis, and since this u1 to uk is 0 addition, we get that each of this ui is 0 by induction hypothesis. For n is equal to k. And therefore, we get that u1 is equal to u2 is equal to uk is equal to uk plus 1 is 0. And therefore, this, that's what we wanted to prove. Therefore, this u1 plus uk plus 1 is a direct sum, because we started with some linear combination of equal to 0 and we arrived that if that is the case, then each of the element in that linear combination is 0. So that's why this is direct sum. And that's it. That's what we wanted to prove. So any doubts here? This was just like understanding the induction. We from here we just arrive at this step of induction, and that's it. Then we were done. That u1 to uk we got 0 because of induction, and this from this equation u1 to uk, so this becomes 0, and we already have right hand side left hand side 0, so this uk plus 1 becomes 0. So all the variables which we started addition of, that suppose this is 0, and then this simple, I'm just explicitly writing this, plus uk plus 1, and then whatever we did is follows as it is. Is this okay?
Yes.
Okay,
We have to
then
see once again.
yes, it just yeah, I mean we use this fact that we use this fact for n is equal to k plus 1, and then we got this, that intersection will be 0, and then once the intersection is 0, each term will be 0. And from here we went back by one step. So we are removing now uk plus 1, and we are only here in u1 to uk, and that is my induction step. And where I'm just assuming that for k n is equal to k, I have direct sum, and once I have direct sum which with each ui, which each small ui in capital ui, then each small ui becomes 0 if their combination is 0. And that's how I got that each u1 to uk is a 0, and the last uk plus 1 was anyway 0 from the intersection itself, from here itself. Oh, so that's it. If there are any doubts, please, otherwise we can stop. Okay then, thank you.